Looks great.
Great.
All right, so our next speaker is Ben Sapp. He is a staff research scientist at Waymo. He obtained his PhD from the University of Pennsylvania with a focus on using machine learning to solve computer vision problems such as human pose estimation. And today we're going to be hearing from him on his work at Waymo for how we can do prediction in complex, interactive, self-driving car scenarios. And with that, Ben, you can take it away.
Cool. Yeah. Thanks a lot, Andrea. That was very nice. So hi, everyone. I'm Ben. I'm a research scientist at Waymo, and I'll be talking about long-term prediction in complex interactive environments. I also want to say thanks, Karina, for bringing up multipath a fair amount. You'll hear a lot more about multipath and extensions of that in my talk as well. So before I jump in, I just wanted to go over a typical autonomous vehicle stack. I think it's been touched upon a few times now. There are three main components. The first is perception, whose focus is detection and tracking of objects to answer questions like, where are things in the world? And then that feeds into behavior prediction, whose goal is to answer, where will things be in the future? And finally, the planner component's goal is to answer, where should we, the ego agent, or in other words, in our case, the autonomous vehicle, go next, which ultimately drives the car. Now, in actuality, there's a lot of interplay potentially between these components, and the flow of information isn't so linear. But for the purposes of this talk, I'll be focusing mainly on the second component, behavior prediction. So this talk, I'll go over some core modeling work we've developed over the past couple of years. But as I hope you can appreciate, modeling is only one aspect of this interesting problem. And I'll try to spend equal time discussing datasets and dataset design, as well as in part 3, I'll discuss different ways of representing the future, motivated in particular by representing interactions between agents. So to motivate our modeling work, one can look at the problem in this way. The challenge for behavior prediction is that there's an enormous number of possible features for a road user, even before we consider the road topology and interactions with others. To illustrate this, here we visualize 10,000 15-second vehicle track snippets obtained from our log perception. So you can see here we have some left and right turns, even a few U-turns. There's some perception noise sort of going back and to the right, and also many, many samples going straight with different speed profiles. So a core solution we devised for this problem is to quantize the space of possible futures into a finite, manageable set of anchor or template trajectories. So here we visualize a set of 128 space-time anchor trajectories that attempt to cover all possible futures. In practice, we obtain these anchor trajectories a priori via k-means clustering. And just to call out, as we just discussed in the last talk that Karina mentioned, CoverNet and other papers use not just k-means, but you can use dynamic anchors, you can use road condition anchors, which I'll touch upon later. So this anchor-based approach forms the basis for our model we call Multipath, and that's published at Coral in 2019. The complete multipath model is really a Gaussian mixture distribution over future trajectories, and is naturally factored into this hierarchy of two types of uncertainty. So first, we decide which anchor trajectories are likely given the scene, and we can informally think of this as modeling intent uncertainty, or in other words, where an agent wants to go. And in the cartoon on the left, maybe they want to go left implicitly because they want to get a burger, or maybe they need to go right implicitly because they need to fill up on gas. Then the second term in our GMM is what we call control uncertainty, or in other words, given an intent, how the agent wants to get there. And at inverse time, this decomposition amounts to classifying anchors and also regressing a trajectory per anchor. The multipath model uses a top-down multi-channel image as input, capturing road elements, a history of agent boxes, traffic light states, speed limits, and more. It processes this input via ConvNet, specifically a ResNet 18 in the paper, to obtain a spatial feature map. Then via differentiable cropping and rotation, we're able to train the model end-to-end and predict in an agent-centric frame for n agents, each with k trajectories for t time steps. So that's good so far. And image-based representations and ConvNets are great for a couple of reasons. Rasterization is a very straightforward way of fusing heterogeneous world state information into one common representation, such as road graph, agent state, etc. It also lets us leverage powerful and well-established ConvNet techniques developed by a large computer vision community for over a decade. But they also come with downsides. So there's this unpleasant trade-off between field of view, resolution of the image, and compute. it's hard to model long-range interactions. That's a classic problem with conf nets. And sometimes it's unclear how to raster rich state information into image form. As for these reasons, we next turn directly towards using the sparse real-world state of the world. So road graph elements, for compactness, we represent as piecewise linear segments, or we can call them polylines, and agent state represented in terms of its original real-world units, position, velocity, box extents, etc. So using Rastate in this way allows for sparse representations, arbitrarily long-range interactions, and no rasterization, quantization problems. But on the flip side, we now need to rethink the model architecture to leverage this. So this new architecture we're calling Multipath Plus, and it starts again with road polylines and agent states, and factors the modeling into separate and explicit encoders for road elements, agent path state, and agent interactions. These are then fused, and then the multipath prediction head, as described before, is applied to output trajectories, likelihoods, and uncertainties for each agent. So this diagram isn't really telling you much. It's fairly generic, high-level architecture of what one could do, and the real challenge lies now in designing these encoders. So before we just do this from first principles, we can look at what others have done in the literature. And so this slide hopefully conveys this is a very hot space where we went through a somewhat exhaustive survey of literature and deconstructed architectures along these dimensions that we cared about. So this also includes a couple of milestone papers we developed at Waymo as well, which are VectorNet and TNT. And some takeaways from this table, well, there's clearly two camps for how to encode the road graph. There's rasterization approaches, and then there's polyline approaches. For modeling a state history for agents, recurrent neural nets are seemingly the majority popular choice. And for agent interaction, it's really a mixed bag. Different methods aggregate neighbor information using convolutions, some kind of pooling, or attention. So in the end, when we were developing Multipath++, we strove for an agnostic, evidence-based approach and built up a framework to try all of these design choices by treating them as hyperparameters. So here's what we found works best. In each category, our design choices overlap with at least one other paper. But what's interesting is that this combination of choices that we came up with is actually unique. So we developed our models on large internal data sets. And by internal metrics, we felt we were doing really well. But we still wanted to calibrate ourselves with the outside world. So for this, we trained and submitted models to the Argoverse motion forecasting competition. And to our satisfaction, we placed first on the leaderboard. So this is a highly competitive leaderboard, many active users, and over 150 total submissions. And in fact, 7 of the top 10 submissions were submitted in the last 2 weeks. So it's important to include a date on these results. And actually, I just looked last night, and it turns out there's a new #1. So we're #2. Gives us something to work on next week. But we're doing really well. So what is the real secret to Multipath++'s success? On the surface, it may seem like we just mix and match techniques from related work. And in some aspects, this is true. In other cases, it was a case of convergent evolution where we developed these things in parallel. That being said, there's many small tricks to eke out the best performance. So I unfortunately don't have time to explain any of these in details, but here's a brief list. So I'll just rattle these off. So fusing encodings via repeated cross-attention, predicting kinematically fusible controls, eschewing static anchors, and then instead we learn anchors during training, despite issues that we have fought before with mode collapse, training on TPUs, employing model ensembling, and non-max suppression. So we can look at some results. In the following, we show predictions color-coded from our Waymo brand green color at 0 seconds in the future to Waymo brand blue color at the Argoverse time horizon of 3 seconds. In these examples, you can see the road graph displayed as polylines, the other agents boxes, the perception track history for the agent that we're predicting, and our Multipath++ multimodal trajectory output. We're predicting 6 distinct trajectories in this model, and we show the trajectory likelihood confidence as transparency value with 100% confidence shown as totally opaque. So here are some more examples where you can see our ability to follow the road many meters in the future, validating our road graph representation. And some more examples. And here you can see some of the challenges of perception track jitter and also the ability to capture very disparate, well-separated, distinct modes on the image on the right. So picking out highlights like the previous slides for a talk like this was actually fairly challenging. I had to sift through an overwhelming amount of non-interactive straight driving on straight roads. So this is more of an honest sampling of the data that we see from the validation set. So Argoverse has been a valuable resource for us for validating ideas, especially core architecture choices, like how to model the road graph and capture multiple feature modes. But still, there's a fairly big disconnect between the data in Argoverse and the data we want in practice to develop and validate real models for driving in the real world. So we can take a step back and think, what do we want from a data set from first principles? Well, roughly, for one, we want the data set to be big enough to leverage high capacity deep learning models. And there's many ways to measure data set size, and people use different measurements of it. But typically, you can think about it in terms of number of unique tracks, number of unique locations in the world, number of hours logged, or miles driven. Second, should be high quality. So we much rather focus on true behavior modeling rather than dealing with biases in perception. So ideally, that will be factored out. We also want to include as much rich information we have about the agents in the world as we might use in practice on a real vehicle. Finally, the data set should have interesting behavior. By our estimates, more than 90% of driving data sampled at random is stationary or straight driving, which is quite boring and easy to capture. Instead, we'd like to focus on the difficult and impactful challenges in behavior modeling, tightly interacting agents, and long time horizon prediction. In both of these, latent semantic intent is crucial, and uncertainty about the future is high. So trying to be as objective as possible, we can categorize existing data sets by their size, quality, and interestingness. Here we show 4 popular real-world driving data sets, and we'd also be remiss if we didn't include TransNet++ for comparison, which is a centerpiece of this workshop. As an aside, TransNet++ is focused more on pedestrians and less constrained open area environments than in dense urban driving domain, and also by our industry standards is relatively small. Given the shortcomings of these existing data sets, we were motivated to develop our own data set, which we call the Waymo Open Motion data set, which we argue is big, high quality, and interesting. So here's some details of that data set. This was a large group effort, as you can see, and we also just published and released this data set in April. And importantly, we're also holding a corresponding motion forecasting challenge this year. And the submission deadline is June 11th. So I encourage you to go to the website, download the data, and submit a model as fast as you can. OK, so now we can look through the 3 important axes that we care about in this data set. So for one, it is definitely big. It has over 500 hours of logged data and over 7 million unique tracked agents, which are vehicles, cyclists, pedestrians. Is it high quality? Well, we cleaned our data with a high capacity offline perception system, which can look forward and backwards in time. The average track length is 7 seconds, which gives us lots of historical context from which we can make predictions. And it includes a lot of rich agent and world state information from 3D HD maps, 3D track boxes, and traffic light dynamic state. Lastly, is it interesting? Well, we have more slides on this later. But it was specifically curated with interactions in mind, and the task is to predict out to 8 seconds in the future, which to our knowledge is significantly longer than any other data set. So to give a sense of the diversity of the data set, on the top row here, we visualize all ground truth trajectories from the validation set in an agent's frame of reference, broken down by agent type. And as we can see, it's definitely not all just straight trajectories, which is good. And on the bottom row, we can see that speed is also well distributed for each agent type. So stats and histograms are no substitute for looking at real data. And here we're going to show a series of GIFs where we train Multipath Plus on the Waymo Open Motion dataset and are showing results on the validation set. So for starters, here's a complex 4-way stop scenario involving interacting vehicles and pedestrians. In contrast to Argoverse, now we're showing, again, 6 trajectories, but for many agents in the scene, out to 8 seconds in the future. In this parking lot example, we see we're able to predict plausible agent futures in this less constrained driving setting. And oh, sorry, let me get a pointer out. At the risk of reading tea leaves, we can say observe this car which is pulling into the parking lot. And we see these sort of tendrils of predictions at times, which indicate maybe we're predicting that he's looking for parking. So here is another example which shows an interaction where the prediction for the car near the red arrow, well, I have my pointer I can show you, It heavily depends on the state of the car crossing the intersection. So it first predicts it's likely to go either left or straight while the vehicle is, before the cross vehicle is proceeding through the intersection. But whiles block the right turn, and then even the straight is cut off. And as the intersection becomes clear again, the possibility of going straight and right becomes available again. And then ultimately, the pose of the vehicle indicates it will follow this car that passes the intersection. And then here is a tight interaction on a narrow road, which creates a natural bottleneck because there's a double car parked vehicle here. So you can see cars coming from the left and the right. Because of this bottleneck, one of these cars is going to have to slow down. As we see, as they get close, the car coming from the left for a brief moment predicts it will yield. Once this car passes, we actually predict nudging behavior around the parked vehicle. Let's just watch it one more time. Cool. Great. OK, so you might have noticed scenes get a little crowded in this data set. Even in this relatively simple example as shown here, note how the per agent future distributions overlap. So what does this really mean? When they overlap, does that mean there's a predicted collision? Can we represent the likelihood of the collision? Are we even confident to say, yes, these agents are interacting? And if so, how do we quantify how much they interact? So for the next part of the talk, I'll discuss this topic, which is hot on our minds, which is how to represent and quantify interactions. So to try and answer some of these questions, let's simplify and distill the issue down to a pair of agents, each side by side with equal probability of turning left and right. In all the work and related work presented thus far, we've represented the output as independent sets of trajectories per agent, which we also are going to call marginal distributions per agent. And these types of marginal distributions can't represent incompatible futures. In particular, for this example in the diagram, it's extremely unlikely that the agent A will turn right while agent B turns left, which would end in a collision. This representation is in particular bad for planning, in which a planner must conservatively assume a worst case scenario. Despite this problem of representation, public benchmarks today only measure per agent trajectory distance errors. And we really wanted to address this principled interaction modeling in the Waymo open data set. And to that end, we created a special challenge track focusing on interaction prediction. We collected an interaction subset of the data specifically by mining for known hard interaction scenarios using domain expertise. So we essentially wrote heuristics to mine our very large corpus of Waymo data for merges, lane changes, unprotected turns, intersection turns, different object class interactions, and then interactions with close proximity or high acceleration. In all these scenarios, we mark the pair of interaction agents that we mined, and that allows us to define joint future metrics to evaluate interaction performance directly. So first, we can look at some of this interaction data where the pair of interacting agents have these, they're circled here. So this is a cut-in case, and then this is a case with a ped-car interaction where the pedestrian is jaywalking in a busy road. And then to motivate joint metrics, let's look at arguably the most popular error metric, which is called minimum average displacement error, or min-ADE. So this metric attempts to be forgiving in the face of an intrinsically unknowable and stochastic future. Each agent gets k future trajectory guesses, and the minimum distance one is reported. So in other words, for each agent, what is the best guess out of k guesses? To extend this to joint future modeling, we use what instead we call joint min-ADE, which forces a single best joint assignment of futures for all agents to be reported. In other words, for all agents in the scene, what is the best joint assignment of trajectories out of k joint assignments? So this metric no longer allows one to pick and choose what the best guess is on an individual agent level. Equipped with joint metrics, we could naively consider joint models of the future between agents. For example, now we can directly model the low likelihood of the agents colliding. A major downside with this naive approach is that it scales exponentially with the number of agents. So even with a handful of agents and a handful of trajectories each, this becomes intractable. Instead of a full joint distribution or the other extreme of a fully independent output representation, we can also consider a factorized conditional distribution as a middle ground. In particular, we can condition on possible future actions of our autonomous vehicle as a form of counterfactual reasoning, like what will the future look like if I turn left versus if I turn right? This conditional form is still tractable while still being useful for planning. So we can train a conditional version of Multipath Plus, which optionally takes as input, as an additional input, a positive future trajectory of our self-driving car. We can run conditional Multipath with and without future conditioning. So on the left, you can see the pedestrian predictions at the intersection are highly multimodal. It might cross the street or continue beside or even in the road. On the right, if we condition on a future in which the self-driving car does not yield in the intersection, the distribution of the pedestrian shifts heavily to either staying stationary or continuing along the sidewalk. And here's another conditional Multipath example where when it's not conditioned, there are broadly two modes with equal probability for the agent. One is coming to a stop right before the intersection, and the other is maintaining speed through the intersection. When conditioning on the STC pulling out in front, the likelihood shifts heavily to favor the stopping mode. So in addition to being useful for planning, conditioning on hypothesized futures gives us tools in order to visualize, quantify, and analyze interactions between arbitrary agents. And this is a paper we have published at ICRA, this ICRA this year. And here is an advertisement. Please come to Kate's full talk on it on Tuesday. So try to bookmark this. She has 12 minutes to give that talk. I'm going to do a very dense one-slide version of it. So here we go. The main idea of this work is to quantify interactivity by comparing marginal versus conditional distributions. So equipped with conditional multipath, we can develop this in a few easy steps. So we focus on a pair of agents interacting in the scene, A and B. And we can first predict agent B's marginal future distribution, which I'll just call P of B. We can also predict agent B's future distribution by conditioning on a particular sample from agent A's distribution, so P of B given A. Next, the question is how, next we define a notion of how much agent A's trajectory has influenced agent B's distribution by looking at how much agent B's conditional and marginal distributions differ. Specifically, we can measure the KL divergence between B's conditional and marginal distributions. Expanded out, that looks like this equation here. And that was a notion of influence for a single trajectory sample from A's distribution. And then to get the total influence A potentially has on B, we can compute the expectation of influence over A's whole distribution, which looks like integrating out in this way. And this is what we call the interactivity score between A and B. It turns out that this derivation is exactly the mutual information between A and B, which is interesting because it's a symmetric quantity, even though we motivated the derivation in an asymmetric way. And another related point to point out is that our models and our notion of interactivity is correlative but not causal. And teasing apart causality is an interesting future work direction. So tying everything together, I have a couple slides, sorry. A couple more slides to go. Using ideas from the paper, we can now quantify how interactive the new Waymo motion dataset really is. So just like the last slide, for each agent pair A, B in the dataset, we can compute the KL divergence between the marginal predictions and predictions conditioned on future ground truth to obtain a distribution of interactivity over the dataset. We can also run this only on the subset of data which was specifically mined and annotated by hand for interactivity. And thankfully, the quantitative interactivity score agrees with the notion that our manually curated interaction dataset is more interactive than any two agents at random. OK, so that concludes the talk. So to summarize, I touched upon models, datasets, interactions. In models, I introduced Multipath Plus, which is our best performing sparse state space model. But keep in mind, modeling is a very hot topic, and these models are constantly improving. In datasets, the Waymo Open Motion dataset is here. So please check it out. I argue it's big, high quality, and interactive. And regarding interactions, try to make a case that we need better representations and better evaluation for interactions. And conditioning on future hypotheses is one useful tool to use. So that's all I have. Thanks. I'm happy to answer questions and leave you with some more fun gifts to look at.
Thank you so much, Ben. Any questions from the audience? I have a quick question while people unmute themselves and start asking questions. So you were mentioning how with this conditional behavioral prediction, you hope that the downstream planner can also make better decisions because it now has a better sense of, if I do, action A, how will that affect my overall interaction with the other agent? Can you talk a little bit more about sort of quantifying that on the data set, and how much better do you actually see the ego agent performing when it knows these conditional distributions?
Yeah, so this gets very interesting, an interesting ball of twine in a val. So since you're positing hypothetical futures, you really only have measured one true future, right? So you can condition on what actually happened, and then we have problems of causality or even collaboration. The model can learn that whatever we condition on always happens. And these are really important things to tease apart. And what you really might want is a data set of counterfactuals, which is say, I want some ground truth of the same scene where two different outcomes happen. So I can measure the fidelity of the model for different outcomes with the same input. So that's extremely challenging. You can resort to simulation for that. And then you have all the problems of sim to real gap. So I can't answer the question. I can just give more problems surrounding that. But that's how we think about it.
Yeah, it's very interesting.
Yeah.
Other questions? I have another question for you.
Sure.
And it's more on the prediction metric side. So I think what was really interesting was this is sort of one of the recent talks I've been to that has started to address prediction metrics that are going beyond just ADE and FDE. And so I was curious if you have other thoughts on how we can incorporate maybe other kinds of uncertainty in decision making, for example, coming from perception, coming from like class label types, coming from all these different sources of uncertainty into our prediction metrics, so we can make our prediction metrics, I think, more maybe more indicative of the overall pipeline in which that they exist.
Oh, interesting. So I haven't thought about how to fold perception uncertainty in. So I guess you could sort of, I mean, you can definitely train with those as extra inputs to models. In metrics, I'm not sure what you want to quantify. So I haven't thought about that. We have thought about measuring uncertainty in a bunch of different ways, and I have maybe I can show one slide on that potentially. We have a bunch of other metrics. We care a lot about metrics design. So in the Waymo open motion dataset, you can come and you can go to the website and check out definitions for these, but overlap rate, so whether we predict collisions, and quantifying things not just with altitude distance, but actually quantize miss rate as a function of velocity, et cetera. And then we like this one very much, which is treating actually prediction more as a detection type task. So you measure precision recall, and importantly, you balance that over different behavior action types. So those are the things we think about in metric design.
Very cool. There's one question in the chat which asks, what topics do you see as the main remaining challenges in this topic area?
Okay, I mean, I think everything I focused on in the talk. So it's really what is the right API in software engineering terminology between prediction and planning, or instead of the word API, what is the right representation to communicate interactions in a tractable way between prediction and planning? So and everything comes with that, with how to evaluate it in a counterfactual sense, et cetera, et cetera.
Great. I think we might have time for one quick question. I'm going to take the person who has their hand raised. Barrett?
So hi, thanks for the great talk. I have a question. So this joint AD is used only as a metric. So have you tried using it as a loss?
Yes. So I alluded to this. So naively, you can do like a brute force joint output space model, and you can do this for a pair of agents. I can't remember if this is in the actual paper, the Waymo open motion dataset paper in the table or not, but you can definitely do this sort of thing. It doesn't scale to more than a couple of agents, though.
Okay, so you see that as an issue. Now, in all these GIFs, it's only single agent prediction done, not joint.
That's
for
correct.
all agents.
Yep, that's definitely correct.
Okay,
awesome.
Thanks.
There's one last question in the chat for you, Ben, but I think we should break here, and we'll see everyone back here in about 10 minutes.
Cool. Thank you.
Thank you.
Thank you, Ben.
Thanks.